first of all, I would like to thank the organizers and Piotr and Jan for all this great work and for all the care and thought given to receiving us here. It's been so far a very, very fun and very interesting conference. And second, I mean, it's really a great honor to be able to talk in honor of Patrice in this day, in honor of his 60th birthday. So, and I mean, I think everybody now here can know the importance of Patrice to the field, and it's really difficult to overstate the importance of Patrice to the field. I mean, he's really one of the people that made all this conference and all this field go and become this way. And at least personally, I mean, I made my career. Andre always talk about how you make your money. So I made my money on ideas from Patrice. First, Salvador came and gave me, oh, there's this idea from Patrice, and then we work a lot, and then oh, something appears, and then Andres come one day and say, oh, there's another idea from Patrice, and then finally I meet Patrice, and then we have an so I mean, I just want to say thank you, Patrice, and thank you for your kindness. It's really nice. Thank you. Okay, so now I'm going to talk about a new work with Patrice. Where's the chalk? Here. Here. So it's about, okay, so it's topological horseshoes for surface homeomorphisms, and this is joint work with Patrice. It's kind of a follow-up on our previous work on forcing theory. And to start, let me define what is a topological horseshoe. So I would say that you can define it on a more general set, but I'm going to assume I have F from S to S, where S is a surface, it's a homeomorphism. And I have some set lambda, and I say that lambda is a topological horseshoe for F if lambda is compact FR invariant for some R the 0, and there exists a finite extension of lambda of FR lambda to some G from some space Y to itself, such that G Y has as a factor the shift sigma from 1 Q Z to itself. With the properties that, okay, so not to get lost, and also we need that for any S periodic point of the shift, you get that there exists a corresponding S periodic point for G, so that meaning that, okay, a finite extension just means that the fiber over lambda has at most, there's a uniform bound and on the number of points that each fiber can have. So any point in lambda can be lifted to at most some m points in Y. And then these two conditions imply, for instance, that F, the topological entropy of F is positive, and the second one will imply that that you have an exponential growth of the number of periodic points for fr. So then this means that if you have a topological horseshoe, what you're going to get is that you get both topological entropy and well, large rate of growth of periodic points. And well, one famous result by Katok says that, for instance, if f is C1 plus epsilon and the entropy of f is positive, then f has a topological horseshoe, so that in some sense, we're talking here, I mean, at least for differential dynamics, studying existence of topological horseshoe is the same as studying positive entropy. And the question we were interested in.
How do you check this existence of this extension?
Which one?
Practical point of view, the extension.
The 1 to G? Oh, how do we? Usually what we do in the work is that you build a topological horseshoe on some covering. And then and it's a compact set, which in your covering is a topological, well, this is the extension G. So
How do you check in the cover? You see things crossing?
Oh, you just see something that there is, you can construct some square like this, and the image of the square does this. And if you see, this is just a topological picture, so if you see this topological picture, you know you have a horseshoe, okay? It's a Kennedy-York horseshoe. So yeah, usually what you need to do is you just need to find a topological set that looks like this, and well, there is this side is the image of this side is the image of that side, and if you see something like that, or any number of legs will give you the Q from the semi-conjugacy. So that's how I usually go.
You require 9 legs all.
Okay, that's a Q legs, not 9 legs every time. Okay, and so the question we want to understand. I mean, having a topological horseshoe is a very good model for the dynamics, but the question here was, in some sense, going the other way around, which is how are maps without topological horseshoes meaning we prepare a criteria which hopefully I can speak a little bit on the end, but it's technical in some sense to describe when do you have a topological horseshoe. And then the idea here is to play, okay, let's try to characterize what are the homeos of what's the dynamics which doesn't have any topological horseshoes. So what can be thought of as simple dynamics. Okay, and can I erase this? Yeah, okay. So, and so problem is we sort of need examples. And just to start, we should concentrate. So we're going to concentrate on the two-sphere because, well, if you're going to start somewhere, it starts at the two-sphere. So we would like to have examples, and then, well, the first example is a conservative example. It's the flow, it's the phase space of the pendulum which is conservative flow on you can think of that as an R2, and then you can just compactify. And what you see is that the dynamics is, okay, you have some singularity here, things rotate here with different varying speeds. This is going to, okay. And then you have some orbits that go from one singularity to the other, and you repeat here. Here you have something similar this way, something similar this way, and then orbits here go like this. This is a good example of something that doesn't have entropy. It's, you can, everybody have seen this picture at some point in their life. It's just, and there's this kind of behavior. This is, well, it's a simple example for conservative things. Well, the other kind of examples is you can have something like a north-south dynamics on the sphere. And this is no longer a conservative example. What you see here is that everything kind of moves from one fixed point to another fixed point. So the dynamics is all concentrated on periodic points. There is a third example that we should take in mind is you could have something like, you can have something like a irrational rotation here in one circle, and then everybody moves from this circle to the other, and here you rotate with some rho, which does not belong to Q. Or you could do something different here. So now you have, the dynamics is on the plane here, and everybody either goes to this rotating circle, which every point rotates with some speed, with irrational speed, or from here it goes down. Or you could do a somewhat different example where you just construct, instead of constructing here something rotating with irrational speed, you can just put some Danjois set, some compact set here. For instance, you can have a Danjois example here, and then you perturb everything to move inside, and then everything either moves to this Danjois set, or it goes inside, and it keeps rotating. And so you only see it as the transitive sets, the Cantor set or the Danjois. And there is a fourth one, which is also interesting to develop, which is kind of an odometer. The idea is that you have some disk D1, which is invariant. And inside the disk D1, you can find some periodic disk D2. And the dynamic sends D2 to the image of D2, which is disjoint from D2, which sends to the second image of D2, and then it sends back this thing. So F3 of D2 is D2. And then you find inside D2 disk, which, well, will move here, and then by taking the F3 power, what you see is a similar thing. You said you had a disk and a periodic disk inside. Then you take the power that fixes this disk, D2, and you see the same picture. You see a disk here, which is a disk D3, and it kind of, again, exchange. So D3 goes to a different disk and then come back. And then you go again, and you see something which is happening again. And the dynamics, if you take the intersectional of these, the dynamics here is going to be conjugated to an odometer. So the dynamics you can actually see in these situations is conjugated to the dynamics of an odometer. And you can construct examples such that this is the kind of thing that appears and is also doesn't have topological horseshoes. Okay, and the question is, okay, how much more complicated can these things be, or what else can you see as dynamical behavior that appears when you have no topological horseshoe? And the idea here is to describe exactly that there's not much more that you can actually see. So to start, I would start with no, I mean, you need some, you need, this.
I know, but, okay, in every disk you have a periodic
point. In every disk I have to have a periodic point. And, but the intersection of all the disks has no periodic point. So the easiest way is just to have this disk, the period of, periodic of period 2, And you have things here which are orientation reversing saddle things, orientation reversing saddles, and then you have the unstable manifold of the saddle goes inside another disk, and then you repeat the same picture again and again. Flip saddles, yes, sorry. Flip saddles, saddles with a rotation number half. And preserve orientation, yes. It's just flip saddles. So let's start with the first theorem. I'll present two structural results. So. The first one is from a previous work, our previous work. It's theorem where I assume that I have F from S2 to S2, an homeo, and I'm going to assume the conservative case, which means that every point is non-wandering for me, so that I have no wandering points for F, and F has no topological horseshoe. I should write this is Frank Sandel, Bedlewo Tal. Then there exists AI, a family of invariant fixed point free topological annuli such that first the union of the AI is dense on the complement of the fixed points of F. So it contains every point, its union contains almost every point which is not fixed. The second thing is that the complement, if Z does not belong to this union of AI,
You said dense somewhere.
yeah, it's dense on the complement of the fixed points.
Well, the fixed point is a closed set, that is a closed set too, so this
Which set? Hmm?
it should be equal instead of
It's,
even that is not very good.
it's,
Well, they're both closed sets.
no.
Oh, no,
No, this is an open set. This is an open set, not a closed set. Okay. And I'm just saying it contains a fixed point set can have interior, so it cannot.
Equal?
No, it's equal. Sorry, equal, not contain. No, it's not equal. It's contains. Okay. Finally. It's the other way around. It contains everything there. I'm saying that I have no wandering points. This is the first. If Z does not belong to AI, then the omega of Z and alpha of Z are contained in the fixed points of F, meaning that every point which is not in the union of these annuli, it's born from singularities and it dies in singularities. And the third one, I'm going to be not very technical. It says that in each AI, there exists rho I from AI to 0, 1, rotation number function defined everywhere for all points and continuous. Meaning that I have these several annuli, and if I look at the dynamics in each annuli, you have an homeomorphism of an annulus, and you can define the rotation number as, I don't think it's been done in this conference, amazingly, but well, everybody, so you just measure how much you rotate inside the annulus, and this function doesn't need to be defined in general, but in this case, it's defined for every point, and it's a continuous function. And the picture that you can get from here, so I say this theorem was first proved by John Franks and Michael Handel for C-infinity diffuse with an area preserving instead of non-wandering points, and then we extended it to the topological setting. Though the proof is usually very topological, so it's infinity, but they use just a small assumption for C-infinity. Most of that should hold in C1. And the idea here, just to have a picture of what you can see, is that when you look at the phase space, is that you have some singularities, and you have orbits that go from singularities to singularities, like this thing. So you have this continuum of things that goes from one singularity to the other, and then everything here, you have annuli A1, A2, A3, A4, A5. You also have another singularity at infinity that we're removing. And inside here, things rotate, and everybody has a well-defined rotation number. So you can look at, oh, there is some subset here that's rotating with speed square root of 2 over 2, for instance. And then you have this region, which is rotating everybody with speed square root of 2 over 2. Or you have another one, which rotates with some larger speed here, or you can have things that rotate, and this drawing is just going to help me. You have this region where everybody rotates with speed a half, meaning that this disk is sent to this disk, and this disk is sent to this disk. And if you want to, you can then repeat the theorem for the powers of f, and you find here, oh, here I have another fixed points, and I have new annuli, and you can construct all the same thing again and keep doing. So in some sense, there is some nice relation. If you look at the picture from the conservative flow, you can see here also there is this annuli, this annuli, this annuli, and there is this big annuli, if you look at in the sphere, that's also having varying rotation speed. Okay, so I think yes, I think it cannot be 0 in any of these points. It's strictly contained between 0. The rotation should be here, open 0, open 1, not 0, 1. So this should be. Let me leave it like that. I think it's true, but let me not commit now, okay? So this is the picture, which is the conservative thing. And now, can we get something similar for the general case? And for the general case, the theorem is as following. You cannot get such a nice, I forgot something here. I have this annuli and the AI are disjoint. So I have a family of disjoint annuli that have that. For the general case, this distinction is going to appear. So this is the theorem, and okay. So I have here F from S2 to S2 homeo, and no topological horseshoe. And let me define omega F prime is the set of points Z which belong to omega of F such that alpha of Z union omega of Z is not contained in the fix of F. Just consider every point which is non-wandering, but I want to consider points such that they don't go, they can go forward in time they can go forward in time to the fixed points of F, so they can die in fixed points, but then they cannot have been born in fixed points. Or you take points that were born in fixed points but do not die in fixed points. I want to exclude from this set all the points that are homoclinic to the fixed point set. Okay? And then the theorem is that there exists a family AI of fixed point free invariant annuli such that in this case I know that the union of the AI contains, no, this is correct, omega of F prime. So this set of annuli contains all of these non-wandering points except the points that escape.
But you were considering homeos for which is?
There are no topological horseshoes.
This is the only hypothesis.
The only hypothesis. I mean,
and then you have an assumption on this set.
No, I have no assumption. The only assumption for the theorem is that F is a homeo that has no topological horseshoe. It's a general theorem about.
And S of F is
What?
Z belongs to
Omega. Oh.
No,
This is alpha limit of Z. Z belongs to the omega of F. Okay. So I should say, because it's difficult to read, I'm saying these are non-wandering points, and just that they non-wandering points which are which are not homoclinic to the fixed point set. That's all. Just all the non-wandering points which that are not both born and die in a fixed point set. And the first thing we have is that the union of these annuli contains all of these points. This is similar to this thing when I say that it contains every point which was not, which didn't have, was not born and died in a fixed point set.
So there's a prime. It's an
Omega prime here, omega prime. The second thing is that if AI, AJ, omega prime of F equals empty, if that means that I don't have these two annuli, if they intersect, they only contain points which are wandering. You cannot have a point which is non-wandering. Exists a function rho I from AI to 0, 1 such that this is the rotation number function, and this is defined. Okay, so it is defined, well defined, and continuous in omega prime of f. So this function is defined and continuous in this set of non-wandering points. And furthermore, if z belongs to AI is recurrent, then rho I of z is different, well, belongs to 0, 1. So if I have a recurrent point, then this recurrent point it can have a rotation number, but the rotation number needs to lie in between 0 and 1. You cannot have a recurrent point which is not fixed, which has a rotation number which is either 0 or 1. So this is a similar statement like this one, but what we lose here, and the important thing.
Sorry, if you don't have a recurrent point, if the point is not recurrent, how do you define it?
You just, in the annulus, you take a compact set on the annulus, and you consider a compact set on the annulus, you go to the lift, and then you see for this compact set, what's the average speed whenever you return to this compact set. And
You're saying in this case it can be 0.
In this case, it can be, and then you take, to have a defined rotation number, you need to take all possible compact sets and say that this thing, the limit exists always for any compact set, and we're saying that in principle, you can have 0 rotation number. These points don't escape to infinity, so they have to return to compact sets infinitely many often. And you can always define a rotation. You can try to define it. It also works here. Okay, and so all these annuli are open, fixed point, free invariant, open, topological annuli. So these are just topological, open topological annuli. Yes, and. What we lost here was the, let me just, these annuli do not need to be disjoint. Now you cannot talk about disjoint annuli. You can have simple examples, for instance, when you have, say, one curve rotating this way, one curve rotating this way, another fixed point here, and the dynamics here is, say, from this side to this side to this side. And then my annuli would have been, our annuli would have been, there is this first annuli in red, and there is a second annuli in blue as soon as I find the blue. These two annuli do intersect. They have this region which is in the intersection of both, but they don't intersect in any point which is non-wandering. Every point which is non-wandering it lies exactly in one. And what you can have is that, okay, I can have points that go from this red annuli to the blue annuli, the points that go in this direction, and but I don't get points that go in the other direction. This is a different result. I'm just saying that there is some sort of order that you can impose on the different annuli. So I mean, you have these different annuli, but then they might intersect, but not in the non-wandering set. And
from what you wrote, they can intersect in the non-wandering, but with this, that point cannot be asymptotic.
Yes, the point cannot be asymptotic to 0. Yes. And let me, and then okay, this is a structure result. It's going to be very useful in proving other stuff, but sometimes it's easier to describe maybe some simpler objects. So when you're talking about the dynamics, you probably want to know a little bit about what are the transitive sets or the recurrent points and things like that. So we have a different result that goes to okay, I need some definition before. Before showing what I want to say, let me define definition. I'll say that say F is topologically infinitely renormalizable over a compact set lambda, and just for this talk, I'll just write here just to say topologically infinitely renormalizable, not write it all the time, if there exists a sequence Qn of integers going to plus infinity, a sequence Dn of topological open disks with Dn plus 1 containing Dn. So it's a nested sequence of disks such that first Fqn of Dn is equal to Dn. So these disks are periodic. You have a period where they return. And Fi of Dn does not intersect Dn for these disks are periodic disks, and they don't self-intersect for up until the period Qn. So the Qn is the first time they return, and they return exactly to themselves. And lambda is contained in the union of these disks. So I have this compact set. It's covered by disks which go forward and return. And so the idea here is exactly the idea we have before, meaning my compact set is someplace here, and I can find first, for instance, a fixed disk that contains this compact set, and then I can find some disk with period 3 such that my compact set is contained in the union of this disk and its iterates, and then I can find some disk with period 6. This goes this way, this way, this way, and now if I look at the return map, I have a disk which do the same, and then you have another one, and another one, and another one. And let me define this for S, F, S to S, ohmu, where S is some surface, and as a consequence, for instance, if F is tier over lambda, F from S2 to F from S2 to S2, then F has periodic points arbitrarily large period. Just because you have, for each of these disks, you have a compact invariant set inside, then by Brouwer theory, you're going to have at least a fixed point inside these disks. A fixed point, a periodic point for these disks. For the return map, you have a fixed point. And now we can state another result. So I have f from S2 to S2 omil, no topological horseshoe. And I have lambda is a transitive set for f. And meaning I just want a compact invariant set which has a dense orbit inside. It contains this set, and then, okay, maybe I could, no. 1, lambda is a periodic point, periodic orbit. There are only 3 possibilities. Then either lambda can be a periodic orbit, which is a simple case. The second case is lambda is an irrationally rotating set. And I'll describe a little bit more what I mean by irrationally rotating set. But keep in mind the second example we had 2 examples where you had some sort of points which were rotating with irrational speed around some fixed points. Okay, and that's more or less the idea of what an irrationally rotating set can be. And the third case is that lambda f is over lambda, meaning that the only other possibility is that you have something like the odometer, which I described here. And just to okay, not that well in time, sorry. And irrationally rotating set, it's usually the following thing. You can find some periodic point. So I have some p, f of p, f2 of p, f3 of p, p equals f4 of p. You have some periodic point which is some periodic point, and then you look at the iterate of f4, and then your set has it rotates for the iterate f4. It rotates irrationally around this periodic point p, and it has some other component here, 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 meaning that you have like 4 different disks if you want. And here you have one piece of the transitive set which rotates with irrational speed around this point P. Then this set is sent to this one, this one, and then back to itself, and everybody is just rotating with irrational speed. It might happen that you have one fixed point here. You could have something like a hedgehog where everybody is rotating with irrational speed, but an irrational rotating set can have at most either one periodic orbit or 2 fixed points. But other than that, it cannot contain any more periodic behavior. So in particular, in this case, if you have 2 fixed points, it's actually that the whole dynamics on the sphere is an irrational rotation, like a pseudo rotation. So excluding one specific case, a transitive set can only have one periodic orbit. Here it doesn't have any periodic orbit, and here well, it is a periodic orbit, and here you can be this hairy periodic orbit, a no periodic orbit with hairs. And a final result, just to conclude, is this is some other application. Now we go to the differentiable case. So I have f from S2, from R2 to R2, C1 diffil, such that df is less than 1. So now I'm considering dissipative diffuse of the plane, and lambda is a stable transitive set for f, then either for any neighborhood of this transitive set, you have a smaller neighborhood of this transitive set, so that you never, if you start inside the smaller neighborhood, you never leave the larger neighborhood.
And you're assuming just determinant of df is smaller than 1?
Yes. Okay. Just that I'm assuming that the idea is, well, for instance, this is to treat the case of Henon maps, dissipative Henon maps, and there is a result by Sylvain Corvisier and Henrique Pujals and Charles Tresser that shows, well, they show more than this. They show much more than this, but for Henon maps, but then they have to have an assumption of strongly dissipative. So it's here you can say, oh, you just need the df is less than 1. But they show that it's tier, but not only tier, this sequence of periods that you see here, Qn. Here, in our case, it can be 3, 2, 5, 3, 2. In their case, they show that after a finite number, it's always 2. You always have period W. And here, this kind of okay, I can have a period multiplying kind of sequence. Okay, and so it took me a little bit more than I expected. So kind of just showed you the kind of behavior that could happen. For the technical points, there are two. So one, the tools. The first one is the stronger result for forcing theory. So I'm not going to be able to introduce this. So this is mostly for the people that already know what forcing theory is. But the idea was before we had this thing where, okay, you have this, I have F, I have I, which is a maximal isotropy. I have F, which is a transverse foliation. So for every F, which is homotopic to the identity in the surface, you can find something which is called the maximal isotropy, and then there is this transverse foliation from Patrice. And you can find an isotropy such that this fixed point set of the isotropy is sufficiently large so that if you take any point which is fixed by F, but it's not fixed by the isotropy, and then you consider yes, it goes around something. So then this is a theorem by François, by Sylvain, and by Frédéric, that you always can find such a thing. And then maximal, because you can start with anything, and then you can have a maximal which is larger than that. So it just says that whenever then you lift this to the universal covering, then the map on the universal covering, if you assume that the complement of the fixed point sets of the isotropy is connected, it's a Brouwer homeo. It doesn't have any fixed points. And a transverse foliation here is a Patrice transverse foliation, which says that you can foliate the complement of the fixed point set of f by leaves that always, when you leave this to the universal covering, these are always Brouwer lines. And the new results say, and then you can define something called transverse trajectory. Or, okay, transverse trajectories, which is, you look at for each point you have the isotropy trajectory, but you can also, in some sense, identify a path in the leaf space for that trajectory, which also works. And this path is what you're going to call the transverse trajectory of f. And the thing here is that the new theorem, just as I said, this is technical for the people that kind of knew this before. It says that if there exists an admissible transverse trajectory with an f transverse self-intersection, f has a topological horseshoe. That means that if you can find, I'm sort of waving my hand here, and I don't know if everybody can read. I'm just saying, if you can define these transverse trajectories, and if you find one of these transverse trajectories that have,
Sorry.
okay,
Can you tell me what the transverse
okay.
is again? Otherwise you're talking just about trees.
So I start with f from S to S, homotopic to the ID, and then I can find I maximal isotopy as I described before. So that's an isotopy such isotopy for F. So it's a maximal isotopy between the identity and F, such that the fixed point set has the property that you can any other fixed point is non-contractible orbit, and then I can find F a fully Brouwer-Lekalvis foliation. Meaning that I have here my surface, assume it's the sphere minus these 3 points, and I can find a foliation here, an oriented foliation okay, I should have all of these in the same color. I have here some singularity, but I have an oriented foliation of my surface. And this foliation has the property that I'm going to lie a little bit, that if I take the path of the isotopy, it's not the path of the isotopy, but something very similar, then the path of the isotopy always crosses each leaf from right to left. So I'm saying that, okay, if I look at this foliation has the property that if I look at the path of the isotopy, it sort of crosses every leaf from right to left. Okay? And then a transverse trajectory is this path. It's not really the path of the isotopy, so this is why I'm
It's a modification of the
it's different. There is it's a path that is homotopic with fixed endpoints to the path of the trajectory relative to the fixed point set, and it's transverse to the foliation. Because it's an isotopy, the isotopy could do this. And then you just, okay, I can find a different path which is qualitatively the same, and you just,
You have to modify the isotopy, you only have to modify
If I-
the path.
yes, you just modify the path. And the path, it's when you lift the path, it starts at the same point of the isotopy and it ends at the same point of the isotopy. When you lift it to S minus fix of I, it starts at the same point and it ends at the same point, and this is a transversal path. And then this is the transversal trajectory. And then what you say, but this lives in an equivalent class, because I can modify it as long as it crosses the same leaves. Okay? And to say that it has a F transverse self-intersection is to say that any two paths, any representative that I pick is going to have a transverse intersection with itself.
Right, so then the conclusion is,
And then if you have any path that has this F transverse self-intersection, then F must have a topological horseshoe. So this is a new criteria for finding topological horseshoe. It's involved in the sense that it needs a lot of previous work, but then when you translate it to the dynamics, you can get nice consequences from there. So this is the main technical tool, and it says, okay, this is the main new development on how you can do that. And then there is a lot of work on constructing the analyte and stuff in that direction. So, but this is, okay, so what now new appeared? So there is a good way of looking at this, and from this constructing exactly that figure. You can, from the idea here, in this case, imagine you have a path that does this, okay, sorry. I'll just draw two leaves here. These are the leaves of the foliation. This is the sphere minus the 2 points. And you have a transverse path that does this. Something like this. So this is a transverse path that does this. Any other path that crosses the same leaves is going to have some sort of intersection, which you see here. So I'm saying that if I have an orbit that does this, I can actually construct this square which has this topological horseshoe, the square that goes back and forth twice.
is what is around this intersection point?
No, I mean, it lives in, it's not an easy construction. I can show you afterwards if you want, but it's not an easy construction. And this one of the tools. The second one, I'm not sure I have that much time to say, so maybe I should stop here. Okay.
In the beginning, when you had such an intersection, in the beginning, I mean, in previous paper, you just produced a subshift inside it. Now you have this geometrical.
In the beginning, we needed this trajectory to be closed. So you needed this to be a periodic trajectory, not. And this is just an open-ended piece of trajectory. So, for instance, we could get the theorem for non-wandering things because you could have at least recurrent things and work from there. And here we don't need, you just say that if you have any trajectory, it doesn't need to be recurrent. It's just an open-ended thing. If you have an intersection, you can construct this shift. I think maybe I should stop here.
Are there any questions or comments?
What's the second technical?
Okay. It's this new. It's a simple. It's not that technical, but it's a nice idea. It's called something called Birkhoff. We called Birkhoff recurrent points and the Birkhoff recurrent classes. So I'll be quick. This is usually when you have a question, it's you should put. But give me. Since you ask, I have 3 minutes or 4, and can use them. And it's just the results are not really just for transitive sets, but the idea is here. I can define a relation between 2 points. I say that there is a Birkhoff connection from X to Y. I'm just giving some notation to understand. If I take a point X here, and I take a point Y here, and if I take any small neighborhood of X and any small neighborhood of Y, there is some point from here that will end up in this way. So I'll say that this is a Birkhoff connection from X to Y. From any neighborhood of X, I can go to a neighborhood of Y. And I can define what is a Birkhoff cycle is something X1 has a Birkhoff connection to some point X2, has a Birkhoff connection to some point X3, has a Birkhoff connection to some point X4, and then at some point you go back to X1 again. So you just have a cycle of connections. And then I can define what is, so to have a Birkhoff cycle, say X, it's Birkhoff equivalent to Y if there exists a cycle with X and Y. So you say the 2 points are Birkhoff equivalent if they lie in the same circle, and that's an equivalence relation. If you have a Birkhoff connection from X to Y, a Birkhoff cycle that contains X and Y, and you have a Birkhoff cycle that contains Y and Z, then you have a Birkhoff cycle that contains X and Z. It's just go to Y, go from Y to Z, come back and go to X again. So, and then you can define what is called a Birkhoff recurrence classes, which is sort of the object that we would like to understand here. It's okay, it's just the set of points which are Birkhoff equivalent. This assuming that a point is Birkhoff recurrent if it has a cycle with itself. You can note that, for instance, this is less than being non-wandering. It's more than being chain recurrent. It lies in between the two. Okay, and for instance, you can see that any omega limit is contained in a Birkhoff class, because you have one single point that does a cycle between every point